Hello everyone. Welcome back to another video of the system design playlist. How you guys are doing? I hope you all are doing great. I'm doing completely fine. So today let's talk about CAP theorem. And firstly, we will discuss what exactly CAP theorem is. We will briefly talk about it. And then we will move to the consistency. After that, availability, and then partition tolerance. After that, we will discuss some trade-offs of CAP theorem, which is consistency and partition tolerance, availability and partition tolerance, and then consistency and availability. What are the practical design strategies in CAP theorem? Also, beyond CAP theorem, which is PACELC. We will also discuss about that. So let's start with the CAP theorem. What is CAP theorem? So the CAP theorem was introduced by Eric Brewer in 2000. Remember, it was introduced by Eric Brewer in 2000. So this was introduced in 2000, and it provides a fundamental framework for understanding the trade-offs, right? And what are those trade-offs? Those must be made when designing the distributed system. Like, these are the trade-offs. So trade-offs consist of like consistency, it should have availability, you should have partition tolerance. So here C stands for consistency, A stands for availability, and P stands for partition tolerance. And this theorem states that it is impossible for the distributed data store to simultaneously provide all three. We cannot provide all these three, we can provide two at a time. Like, either we can provide the consistency and availability, or we can provide consistency, partition tolerance, or we can provide availability and partition tolerance, right? But we cannot provide consistency, availability, and partition tolerance at the same time. So here C stands for consistency, means like every read receives the most recent write or an error. Either it will receive a most recent write, the same one, or it will receive an error. We will discuss more about it. And then it will like, we have availability. A stands for availability. Every request, like, what is the request? Either you are reading something or you are writing, so it receives a non-error response without guaranteeing that it contains the most recent write. And then we have partition tolerance. Here P stands for partition tolerance. So the system continues to operate despite an arbitrary number of messages being dropped or delayed by the network between the nodes. So let's discuss more about CAP theorem. In this video, we will explore all the three pillars of the CAP theorem: consistency, availability, partition tolerance, and also we will deep dive into the trade-offs as well. Before getting started with the consistency, let's first talk about the viewers. I think I have now reached up till 10 videos in the system design playlist. So do like, share, and comment below, and also do subscribe my YouTube channel. Those who are new to this channel, let me tell you that I have uploaded up to 10 videos of the fundamentals of system design in this playlist. So now let's discuss about consistency. What is consistency? Consistency ensures that every read receives the most recent write or an error. Either it will receive the most recent write or it will receive an error. So for example, this has done some write operation on this database and you are receiving some value X. Okay, so this will be reflected on each and every database which is connected to this horizontally. So either you will receive the value when this will reach, when this computer B, let's say this is A and this is B and this is C and this is D. So when you are doing simultaneous operations, you are writing something, and when you are trying to access that value, you will receive the latest write. So this will also receive the value X. This is also going to receive the value X. Either you will receive the latest write, either you will receive the latest write, okay, or you will receive an error, or you are going to receive an error. Means the change is not reflected here. So the same change is not reflected here. Means inconsistent. Okay, so every read receives the most recent write or it receives an error. So in a consistent distributed system, if you write data to node A, suppose this is node A So you are writing some data here. A read operation from node B will immediately reflect the write operation on node. So this is going to show the immediate reflection. You can see the immediate reflection here when you are going to access this node. Let's say this is node B. Okay, this is how it works. So consistency is crucial for applications where having the most up-to-date data is critical, such as for example, we have financial system. Here consistency is very important, right? Like if I have done any transaction, or if I am doing debit or I am doing credit, let's say I am doing debit of 500 rupees, so it should be reflected in my bank account, and it should also be reflected in each and every database simultaneously. Like if I want to access that 500 using State Bank of India, for example, I am using SBI, so it will be shown using YONO app. For example, I am accessing through the YONO app, it is reflected on YONO app as well. And if I am accessing through let's say any UPI, or I am using PhonePe, so if I am using PhonePe, it will be reflected there as well. Like you have like 500 debit, okay, this will also reflect in both the places. This is termed as consistency. Let's talk about availability now. So what do you mean by availability? Availability guarantees that every request, what is a request? You are doing read or you are doing write, it receives a response. Every request, none of them will receive an error. Okay, each and every request, for example, this is receiving value X and value Y, and this is going to receive some value Z. So the availability is very high. You are receiving some data, right? You are not receiving an error. You are receiving something. Every time you request a data, every time you write or you read, you both, every time, like you are receiving a data. Okay. This means that the system remains operational. The system is operational every time. It is always operational, and it also ensures that it is responsive. So we say that we have very good services. How we ensure that? We have the availability of 24/7, and there is very less downtime. There is very less downtime, right? So based on that, we can say that our system is available 24/7. And availability is also very important for those applications which need remaining operational at the time. So for example, you have retail system. Okay, so in retail system, the availability concept is very much used. Retail system uses availability. Now let's discuss about partition tolerance. What is partition tolerance? So partition tolerance means that the system continues to function even if the network partitions, okay, even if the network break down or it get to a partition, so the system continues to function. That means partition tolerance. So here nodes cannot communicate with each other. Nodes are not communicating with each other. This cross shows that nodes are communicating with each other. Okay, and it also shows that a system continues to work despite failure in communication. Suppose this is not operational. This one is not operational, and so the communication will not stop because this is connected to this node, and this is connected to this, and this is connected to this, and these both are interconnected to each other. The functional part of the model will work. It will never stop. This is known as partition tolerance. Even if any of your component goes down, or there is a partition tolerance, there is a network breakage, the system will still continue to work despite failure in the communication. So if I talk about partition tolerance more, partition tolerance is essential for a distributed system because network failure can happen anytime. As you know that network failure can occur. So it should be partition tolerant, and a system that tolerates partition can maintain operation across different network segments. This is very important, and P stands for partition tolerance here. Now let's talk about CAP theorem trade-offs. Okay, so we have consistency, we have availability, and we have partition tolerance. We have understood what is consistency, what is availability, and what is partition tolerance. So the CAP theorem asserts that in the presence of a network partition, a distributed system must choose like whether it is consistent, available. You can choose any of two, like you can choose either consistency or availability, right? Or you can choose whether it is consistent or partition tolerant, or you can choose whether it is available or partition tolerant. So you can choose either of two, right? We cannot choose all of them. First, let's discuss about consistency and partition tolerance, CP. Okay, so these systems prioritize consistency and tolerant network partitions, but at the cost of availability. Here we are not thinking about availability. Let's say our system is not that much available 24/7. Let's assume that it is not available 24/7. So we are compromising availability here. During a partition, the system may reject some requests to maintain consistency. So in previous figure, we have understood that in availability, it was creating a response every time. It was giving a data while we were requesting every time. Okay, but here we can compromise in according to the consistency, because we have higher priority to consistency and partition tolerance. So what happens is, in traditional relational databases, such as you have MySQL, you might have used MySQL, right? We have PostgreSQL as well. We have PostgreSQL. In these databases, when these are configured for strong consistency and prioritize consistency over availability during network partitions. So what we do is we are prioritizing consistency over availability. So while there is network partition, we are giving more priority to consistency. If I talk about banking system, for example, we have banking system, right? We have some banking system. So banking system typically prioritize consistency over availability, because the data accuracy is more important and critical than the availability during network issues. And so let's take an example in banking system as well. You have ATM, you might have used automatic teller machine. So ATM network for a bank, there is a network connected to the ATM. When you withdraw money, the system must ensure that your balance is updated accurately across all the nodes. So when you are withdrawing money, it should ensure consistency, that it should reflect on other nodes as well. But we can here compromise the availability, so we can ensure a consistency here. And it is also partition tolerant as well, even if there is a network error occurs. So either the transaction will happen or it will not happen simply, right? So here it is partition tolerant as well. Now let's discuss about the second trade-off, which is availability and partition tolerance, AP. These system ensures availability and can tolerate network partitions, but at the cost of consistency. Here we are compromising consistency. Let's say our system is inconsistent. Okay, we are not prioritizing consistency here. So during a partition, different nodes may return different values for the same data. For same data means like you are receiving some data A and you are receiving some data A again. So different nodes may return different values. Suppose it is returning 2 for this and it is returning 3 for. Again, when you are accessing A, it is returning a value 3. Different values, right? And NoSQL databases like you have Cassandra, you have DynamoDB. These are designed to be highly available and partition tolerant, potentially at the cost of strong consistency. Now let's talk about an example. We have an example of Amazon. So Amazon shopping cart, how it works, right? Amazon shopping cart. Okay, so the Amazon shopping cart system is designed to always accept the items. It always accepts the items and prioritizing availability. It is prioritizing availability over consistency. And when you add the items on your Amazon cart, the action almost never fails. It never fails. Whenever you go to website and you search for some product, select that product, add to the cart. So it never fails because it is prioritizing availability. Even during high traffic periods like Black Friday. So Black Friday was a high traffic day. Like we consider this as the day where there was a very much breakdown over the internet due to high traffic. So let's consider it as a Black Friday, means there is a lot of traffic on that day. Okay, even then your shopping cart doesn't compromise. It is available for you. So we are not prioritizing consistency here. We are prioritizing the availability, and also we are prioritizing the partition tolerance. Even if there is a network failure or anything occurs, so your system will still keep on working. It will not fail. Now let's talk about the CA, which is consistency and availability. What is consistency and availability mix? Means we are not prioritizing the partition tolerance. Let's say if there is a failure or if there is a network breakage occurs, so the system, let's say, stops for some time. Okay, we are compromising with that. In the absence of partitions, a system can both be consistent and available. So however, like network partitions are inevitable, right? We cannot resolve them. In distributed system, they can occur anytime. Like you have a network breakage, there is some disaster, anything. So network breakage can occur any time, which makes this combination impractical. For example, let's take an example of a system. So single node database. We are using here a single node database. Okay, we are using here single node databases. So in the single node databases, these can provide both consistency and also availability, but these aren't partition tolerant. So in a distributed setting, this combination is theoretically impossible. It is we can say that it is theoretically impossible, right? It is impossible theoretically. We cannot ensure that. Now let's talk about the practical design strategies. So the first practical design strategy is eventual consistency. What does it mean? It means that, for example, systems where immediate consistency is not critical. Immediate consistency means immediate reflection on each and every node. Suppose you are doing transaction and you need reflection on each and every node. So which is not important for us. It is not critical. For example, you have a DNS. Okay, you have a DNS or you have content delivery networks. So it is a part of eventual consistency. And the second one is strong consistency. What does it mean? Strong consistency, and what is the difference between strong and eventual consistency? Let's look at it. So the example is systems which require high data accuracy. Remember, you need high data accuracy here. You need high data accuracy. Like you have financial applications, you have inventory management. You can't even at the cost of any error, you can't compromise your security. You can't compromise the data feeded in the databases, right? So you can ensure that it should be consistent, but you cannot say that like data is something different which we don't want it to feed. So this is how there is a difference between strong consistency and eventual consistency. Here eventual consistency means that you don't need immediate consistency. This is not critical, right? You just need eventual consistency. Like you can check the reflection after some time. You can check the reflection after a period of time. So for example, you have DNS and content delivery network, and here we have the financial applications and inventory managements. And then we have tunable consistency. What does it mean? Let's look at the example. So applications which need different consistency level for different operations. So we have a cart, right? We have a cart on Amazon store. We have a different consistency for the cart. Suppose there is an e-commerce platform where the order process requires strong consistency. So here strong consistency is required for the orders, right? It requires strong consistency. But product recommendation, can tolerate eventual consistency. It can tolerate eventual consistency. And then we have quorum based approaches. What does it mean? Let's take a look at the example. Systems needing a balance between consistency and availability. So often used in consensus algorithm like you have PACELC and RAF. Now, if I talk about PACELC, what does it mean? Why do we even studying this? So while CAP is a foundation, it doesn't cover all the scenarios, right? Daniel Abadi proposed the PACELC theorem as an extension by introducing latency and consistency. So they have also introduced latency and consistency. Like CAP theorem wasn't enough, so they introduced latency and consistency as well. These are the additional attributes of the distributed system. So if there is a partition, let's say there is a partition P, and the trade-off is between availability and consistency. So the trade-off is in between availability and consistency. Okay. Else, like if there is a partition, so there is a trade-off between availability and consistency. Else, the trade-off is between latency and consistency. So else, the trade-off is between latency and consistency. Here L stands for latency and C stands for consistency. So this theorem acknowledges that even when the system is running normally, when your system is running fine, there is a trade-off between latency and consistency. The trade-off can also occur in between latency and consistency. So like in conclusion, we can say that CAP theorem is a powerful tool which is used for understanding the inherent trade-offs in the distributed system design. It's not about choosing the best property, but rather about making informed decisions based on the specific needs of your applications. So by carefully evaluating the CAP trade-offs, you can architect a robust and resilient system that delivered the right balance of consistency, availability, and partition tolerance. This was all about this video. We have come to the end. So in this video, we have discussed about the CAP theorem, consistency, partition tolerance, availability, and we have also discussed about a few trade-offs like consistency and partition tolerant. We have a CA and then we have a AP, right? We have discussed about all these things, and we have discussed about PACELC. Why do we need a PACELC? Like it was introduced for latency and consistency. We have discussed all these things. I hope you guys like this video. Do mention in the comment section which part do you like and what is not like any question you have, which is not coming to your mind, like you are not able to understand that. Just mention in the comment section. I will try to answer all the questions, and hit the like button, share the video as much as possible as you can because it supports me as well. And do subscribe my YouTube channel. We'll see you in the next video. Till then, take care. Bye. Thank you.